So we're recording. Good morning. Sorry about yesterday. Had a big problem with the internet. Some of you got my emails, some did not because they were at work. So I'm very considerate. I usually keep you updated. And my second email, about 20 minutes later from my first email, I asked you to just go log out. But evidently I was outside the house. The email did not go through. So it went through later. But I was really thoughtful. I sent you an email. Anyway, I got my internet taken care of. And then when I started my video, when I recorded my video yesterday, something happened to my computer like at the 29 minutes. So I lectured for like an hour, not 29 minutes for the video. But for some reason, I looked at my screen and everything was shut down. So welcome back. Hopefully today will be better. Yesterday, I ended the meeting with this example, Theorem 6.4.4, called the Poincaré-Bendixson. I don't know if you saw it. It says, suppose R is a closed bounded region of the plane enclosed by two simple curves, mu1 and mu2. If R is a free of equilibrium solutions of 6.41, that was our differential equation system, and there is a trajectory confined to R, then either C is a limit cycle or it spirals to a limit cycle. Okay? So I did this example yesterday, 6.13, it's in the book. We have x prime equal y plus x, 1 minus x squared plus y squared, and y prime equal that. We know that 0, 0 is an equilibrium solution. So if you linearize, you will get this system here. So if you look at A and you look at the eigenvalue of it, you will get the eigenvalues to be 1 plus minus I. So that means the origin 0, 0 is unstable because the eigenvalues have a positive real part. So, but then we said we're gonna try to dig deeply into the system and see if the origin is not stable, that it's a repeller, where do they go? So where do solution go? So what we did is I looked at x equal r. We looked at x equal r cosine theta, y equal r sine theta, turn out to be r squared equal r1 minus r squared, and theta prime equal -1. So what happened is, for r between 0 and 1, r prime is positive, and r goes to 1 as t goes to infinity. How do we know that? Because the solution equal 1 over square root of 1 plus c e to the minus 2 theta. That is the solution for this system. You do partial fraction. As you see, as t goes to infinity, r goes to 1. So let's say this is the circle 1. R goes to 1 means what? X squared plus y squared equal 1. So that is x squared plus y squared equal 1. Let's see, if r between 0 and 1, that you start near the origin, you spiral away from 0, 0 because it's unstable, but you approach this limit cycle here, which is x squared plus y squared equal 1. Now let's take a look at r bigger than 1. If r bigger than 1, then r prime is less than 0. That means r is decreasing to 1. So you start here, and it's going to decrease to here. So therefore, x squared plus y squared is the limit cycle. So even though the origin is unstable, solution spiral toward the periodic solution x squared plus y squared equal 1. So what I'm saying is that this system has a periodic solution. which is x squared plus y squared equal 1, which is a unit circle. Okay? Any question about that? That's a good review of what I ended up the video with last time. Any questions?
The video done yesterday when you were doing the proof for theorem 6.4.2.
Right.
I'm
Oh,
just I'm just
oh,
that's where
is that where I stopped?
yeah, that's where the video stopped. You were in the middle of proving 6.4.2.
Okay. Well, I'm going to ask you to finish it. It's in the book, right? And so what the theorem says, so we have x prime equal to pxy, y prime is qxy. This is a planar system. That means two-dimensional system. This does not work for higher dimensional system. And we said if del p over del x plus del q over del y is either less than 0 or bigger than 0 for all x, y in some open set U, then the system admits no periodic solution. Or limit cycle. This is what the theorem says. Okay? So that means it does not change sign. Okay? So what did we have here? We have so this is a P and this is a Q. So del P over del X is is 1 minus x squared plus y squared. Okay? Minus x minus 2x times x plus y. And del q over del y is the same. Is 1 minus x squared plus y squared plus, so this is then the derivative of that. Okay. All right, so let's see, did I get this correct? It is the derivative of this plus the product is u prime v plus x times minus 2x. Okay. So the derivative of that with respect to x is minus 2x. And then this is 1 minus x squared plus y squared plus y times minus 2y. So if you add them up, you get a bunch of garbage. It's neither positive nor bigger than 0. So you don't know. So no conclusions. No conclusion. Because if you add this one to this one, you're gonna get a lot of garbage. So actually, if you add it up, you're gonna get 2 minus 2x squared plus y squared minus 2x squared minus 2y squared. So this is 2 minus 3x squared plus y squared. You see, it could be negative, it could be positive. So you cannot draw the conclusion that there is no periodic solution. But our analysis using the polar coordinate verified to us that even though the origin is unstable, solution spirals toward a limit cycle, which is x squared plus y squared equal 1. Okay? All right, I'm gonna drop it here for this chapter. Now, we're gonna move on to chapter 7, and that will be the last thing we'll discuss. And this is one of the most important chapters. Any question about this here first? Any questions? All right. Okay. Chapter 7. Lyapunov functions. I'm going to call it functions as singular. Okay, because I mean, it's up to you how you find it. I don't know if you ever looked me up on Google search or something, or you followed my research. You can see I made a living doing research on Lyapunov functions. I think I had about 181 publications in refereed journals, and I would say half of them have the title Lyapunov functions in my research papers, articles. And you wonder, you say, well, Dr. Raful, this was an old subject. Yes, it was an old subject. In 1892, a Russian mathematician by the name motion at his name is Alexander Mikhailovich Lyapunov. So we go by his last name. He wrote his PhD thesis on energy function. The thesis called the general problem of stability of motion. And he ended up, we as mathematicians later on called it Lyapunov functions to honor his contribution. Before it was called energy function. Like, remember when we use the energy function? Can anybody remember? We talked about it before, and we gave it a physical term, like physics. Can anybody remember? What did we say? It's the sum of two energies. Can you remember what they were?
Kinetic and potential.
Kinetic and potential. So we've already talked about it, but we never used the name Lyapunov. We called it energy function. Well, those functions that we called energy function, they will serve as the Lyapunov functions. So Lyapunov says, if you have a system of differential equations, regardless whether it's autonomous or not, whether it's planar or n-dimensional system or scalar, if you can find an energy function, well, energy function has to be positive, and if its derivative with respect to time is less or equal to 0, that means the system is somehow stable. But the question is, if there exists a function, v, so you have to come up with the function Lyapunov functions. Okay? You see what I'm saying here? So Lyapunov functions, we usually donate it by V, capital V. I don't know why. You would assume they will call it L, but no, they use the name V, Lyapunov functions, and I follow the same notation using V. So Lyapunov function is an unknown function, but if it exists, it gives you a great result. And in this chapter, we're going to define what Lyapunov functions, how it relates to a dynamical system, finding the equilibrium point, and then constructing a Lyapunov functions and differentiating it with respect to time along the solution. And if it's less or equal to 0, the equilibrium point is stable. If the derivative is bigger than 0, the equilibrium point is unstable. So I'll give you two edged swords. Okay? All right, so let us start. Let the function v be from 0 to infinity across d into Rn. Okay? No. Into, 0 to infinity. And a d is a subset of Rn. And this is time. Okay? So this is time. So basically, v is v of t of x. You see what I mean? T belong to 0 infinity, and x belong to Rn, is a vector. Okay? Now, we're going to let another function, c, from 0 to infinity into, what the heck? Let's see. Be a function across into, so we have this function, c, I think I must have said something to trigger my phone to go crazy. So let's say we have a c, some function in terms of x and so forth. So now let's see, we want to evaluate vt psi of t. A psi here. Okay? All right. Now it's a term of psi. All right. Then vt of psi, if I want to differentiate this. So remember, this is a function of Rn. So it's going to be del v, okay, over del x1 times c1 prime of t, c1 prime of t plus del v over del x2 times c2 prime of t plus del V over del xn Cn of t plus dV over dt. So this is by the chain rule. Okay, this is by the chain rule. All right. Now, so this is using the chain rule. So now let's take a look at, consider x prime equal f of tx. Okay, is t bigger or equal t naught bigger or equal to 0, where x is x1 to xn and f is f1, f2 to fn. So basically, using what we just did, we get dV over dt is equal to del V1 over del x1 times x1 prime plus del V over del x2 prime plus del V over del xn prime plus dV over dt plus del V over dt. And this is equal del V over del x1 f1 plus del V over del x2 f2 plus del V over del xn fn plus del V over del t. Okay? So this is the derivative of V along the solution. Let me give that equation a name, 7.11. Okay? Along the solution of 7.1. Okay? Now, if V is independent of T, contain no T explicitly, then dV over dt is del V over del x1 f1 plus del V over del xn fn. So this term will go away because it is 0. Okay? And this is called autonomous. So this is mean V is autonomous. That means it has no T explicitly in it. It does not contain T. Okay. All right. So if dv over dt is less or equal to 0, right? That means energy is dissipating. Then we may conclude results about 7.1.1. We will get into that in details. Okay? Any questions? So let's do an example. I think we are due for an example. So let's take a look at x prime equal to x squared minus xy. Y prime is y minus x squared y. Let's say I take let v of xy equal to x squared plus y squared. I'm just coming up with one. Remember x depend on time, y depend on time. Then dv over dt is del v over del x times x prime plus del v over del y times y prime, or you do it from here right away. Or this is 2x x prime plus 2y y prime. And that is 2x times x squared minus xy plus 2y times y minus x squared y. And if you can get anything out of it, you're very lucky. Okay? So for now, this is what the solution looks like. Now, in my previous discussion, I used x1, xn because I don't have enough alphabet x, y, z to go around. All right? Any questions? Okay. Now, there is a lot of discussions in the book that I am going to skip for now. I don't need it. Okay. Okay. Recall if x star equal x1 star, xn star is an equilibrium solutions of 7.1.1, then we may translate it to the origin by x star equal to x minus x star. Okay? So you see this here. If x equal x star implies x star equals 0. So it became 0. So you can translate it. And so x equals 0 is called the zero solution. The zero solution of x prime equal f of t x, okay? So we always assume this in the back of our head, that any equilibrium solution can be translated back to the origin. So that's an important, because we want to talk about that solution. Okay? Any questions?
Just a quick clarification question. So,
Sure.
since we can translate any equilibrium solution to the origin,
Mhm.
then hypothetically we are working with some system
Yeah.
and we want to look and examine the stability of each solution. We would translate the system to each equilibrium solution being the zero solution and then examine the stability.
Right. And then study the stability of the new system.
Okay. Just
Then
want to
you,
double check.
then you will be studying the stability of the new system, but the stability of the zero solution of the new system, right?
Okay.
Because because the new system, okay, because x star for this system became 0 for this system. You see what I mean? So you will be looking for this. You'll be working with this one after we translate the whole system. All right? So look, because if x star equals 0 is asymptotically stable, what does that mean? That means x equal x star. So that means x star is asymptotically stable. So if x star x tilde equals 0 is asymptotically stable for this system, then put x tilde equals 0, you get x equal x star for the old system. That means it's asymptotically stable. All right. Any questions? So if you look at x prime equal x minus xy, y prime equal y, so you have y equals 0 and x times 1 minus y equals 0. So you get x equals 0 and y equal 1. So if x equals 0, y equals 0 here. So you get 0, 0, because if x equals 0, y equals 0 here will work. Otherwise, it will not work. If y equal 1, then what is x? So this is the question you need to ask. But y equal 1 to this system here. So we get y equals 0 from here, x 1 minus y equals 0. So we get, so if x equals 0, then y has to be 0 because they both have to be 0. If y equal 1, this is not a solution, okay? So the only solution here is 0, 0, okay? And you can see other solution. I mean, you can look at the predator-prey model, right? And you can translate it and so forth. I was trying to give you an example where the x times 1. How about if I use y minus x here? Let's see. So we have x 1 minus y equals 0, x equals 0, or y equal 1. So we have y minus x equals 0, y equal x. So if x equals 0, y is 0. So we have 0, 0. If x equal 1, if y equal 1, then x is 1. So we have 1, 1. So there we go. So how would you translate this to the origin? So you're gonna let x equal to x minus 1, y equal y minus 1 for this one. So you have x tilde y tilde prime equal to x prime y prime. That is x minus, that is x prime is 1 minus y minus x, and that is, what is x? That is x star. X is x star plus 1 times 1 minus y star, and y minus x, y is y star plus 1 minus x, and minus x will be minus 1 minus x star. So this is your new system. Okay? So you replace all this. So your new system becomes equal to minus y bar times 1 plus x bar, y prime bar equal to y bar minus x bar. Okay? And you will see now 0, 0 is a solution for that system. Now 0, 0 is so now 1, 1 became 0, 0. Okay? So all right. So there we go. This is how you do it. So now you work with this one. Okay? All right. I'm going to flip the board. Let's try a spring problem on page 235. So we get mx second plus bx prime plus kx equals 0. So I'll consider the damped harmonic motion depicted in figure 7.1, where mk and are constant, and there's a typo in the book. A should be b bigger or equal to 0. X is the displacement of the mass from its equilibrium position. Then if we apply Newton's second law to all forces acting on the system, we arrive at the second order differential equation, this one here. So this is a friction here. So if I take x1 equal x and x2 equal x prime, then I get x1 prime equal x prime equal x2 and x2 prime equal x second equal to minus b over mx prime minus k over mx minus b over m. What is x prime? X prime is x2 minus b over m. What is x? X is x1. So we have the system x1 prime equal x2 and x2 prime minus b over mx1 minus, oh, this
Shouldn't
is
it
k,
be? Yeah, I was about to say.
minus k over m x1 and minus b over m x2, right? Okay. Any questions? Why don't you go ahead and find the equilibrium solution for this system? Find the equilibrium solution. All right, as you can see, the origin, so the equilibrium point, x1 prime equals 0 implies x2 equals 0. So then we have minus b x1 over m minus k. Minus b over m x2 equals 0. So x2 equals 0 implies x1 equals 0. So the origin is the only critical point. Okay. All right. So before I do that, let me do two definitions. Okay. So then I will get back to this one. Definition 7.1.3. This is very delicate. Let D be an open set of Rn containing 0. Mean the origin. Why 0? Because this will be critical point. A continuous autonomous function V from D into 0 infinity. Look at the range. The range of D is always of V is always positive. You see that? Is a positive definite so this function V that doesn't autonomous mean does not depend on time. Autonomous. And it goes from a subset D of Rn that has the origin in it. And it's the range of it is always bigger or equal to 0, not negative, is a positive definite. I'm going to flip the board. Positive definite if V0 equals 0 and Vx bigger than 0 for x not 0. Okay? Any questions? Remember, this is the equilibrium solution. This, for us, for differential equation, this will be the equilibrium solution. Now, if x star is the equilibrium solution and you don't want to translate it to 0, then this will be Vx star equals 0. All right. Another definition. Okay, now the function V is said to be negative definite if minus V is positive definite. That means V0 equals 0 and minus V is less than 0. This is what it means. Mean minus V is positive. Okay? That means V0 is positive definite. That means minus V0 equals 0 and minus V of x is bigger than 0 or x different than 0. That means V0 equals 0 and V of x is less than 0 or x different from 0. You see what I mean? This is the implication. This is the implication of it. Okay? All right? Okay. Now, another important definition. Definition 7.1.4. Let D be an open set in Rn and 0 belong to D. Let V from D into 0 to infinity have continuous first partial derivative derivatives. Now, if V is positive definite, if V is a positive definite and V prime of x of t is del V over del x1 f1 plus del V over del xn fn is less or equal to 0 for tx in t0 infinity cross d and x different than 0, then V, then I'm going to continue here. Then V is called a Lyapunov function. Lyapunov function for system 7.1. So for the differential equation. Okay, this is a very, very important. So what does it mean for V to be Lyapunov function of a system at the origin? It means V0 equals 0, Vx positive, and V prime along the solution has to be less or equal to 0. Then it's a Lyapunov function for this system. Okay? All right. Now, if V prime is less than 0, strict inequality. Here, we said less or equal to 0. If it's strict, then V is said to be a strict Lyapunov function. Just want to make sure. A strict Lyapunov function is said to be a strict Lyapunov function for 7.1. So we will get not only stability, if this hold, we'll get asymptotic stability. Okay? Any questions? So here's back to the example. Back to this example. All right. So here we have 0, 0 is an equilibrium solution. Okay. So I am going to let V of x1, x2 equal to A, okay? A x2 squared plus B x1 squared. Now where A and B, let's see, does our system have B? Yeah, the system have B. I'm gonna take A and C, where A and C are positive constant to be determined. Okay? Why don't you go ahead and compute V prime? Compute dV over dt. Go ahead. This one. Take a few minutes and do it yourself and see what you can get. All right. So again, this is 2A x2 prime plus 2C x1 prime. That is 2A x2. What is x2 prime? Minus k over m x1 minus b over m x2 plus 2c x1 prime is x2. You see what happened? So this is minus 2a times b over n x1, x2 minus 2ab over n x2 squared plus 2c x1, x2. Well, first of all, I need you to see that, okay, I went ahead of myself. First, v0, 0 is 0, and v of x1, x2, positive, 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 positive is bigger than 0 for x1, x2 different from 0. So that means v is a positive definite. V is a positive definite. So I got a little bit ahead of myself. Now we're trying to show its derivative is less than 0, so it will be a Lyapunov function. Okay? All right. So remember the mixed term x1, x2 are trouble. But we can choose A, so the two term is it A or C? You can choose A and C. I really don't care. We can choose A so that the two terms cancel out. Okay? You see what I'm doing here? Okay? So set A equal 1, then we want minus 2b over m equal 2c. This implies that no equal the opposite. We want this 2c equal 2b over m. So that means c, we want them to be the opposite. So c is b over m.
Could you try again?
Excuse me. My goodness. So c is b over m. So if this is the case, then dv over dt is minus 2b over m x1, x2 minus 2b over m x2 squared plus 2b over m.
Dr. Raful, I think you replaced your k with a b again. Because it should be c equals k over m.
Okay, so this is minus k over m x1, right? x2 prime, yeah, sorry, minus k over m. K over m. So we want k over m, k over m So it's minus, so dv over dt is minus 2 k over m x1 x2 minus 2 b over m x2 squared plus 2 k. Look at that. This and these go out. Because x1, x2, because x1, x2 could be positive, negative. And we want this derivative to be less or equal to 0. But these two terms cannot make up their mind. So I chose accordingly A and C so I can get rid of them. You see? By doing so, so this is now minus 2b over m x2 squared. Wow. So what is my Lyapunov function? Vx1, x2 is, I chose A to be 1, x2 squared, and then C was k over m. There, this did the job for me. You see what I did? So this told me, so this is less than 0 if B is positive. Okay? Now, if B equals 0, if the system has no friction, that means B is 0. That means 0, 0 will be stable. Later on, we will see, we will show that. All right. So what did we do? We showed V by taking it like this. All right. So now, if I don't translate my system, if I look back at my system, remember what my system was x second plus b over m x prime plus k over m x equals 0. Let's say, forget about this now, and let's say I take my v to be so if I take v of x to be one half mx prime squared plus 1/2 k x squared. So what is that? That is kinetic energy and that is potential energy, spring potential energy. I can do it this way. I did not have to translate my system. As I said before, this V is the energy function. Look at it. Now let's take a look at, look what we got here. Let's take a look. So we know that V0 equals 0, x equals 0 is a solution, and V of x is positive for x not 0. Let's take a look at dV over dt. That is m x prime times x second plus k x prime. Okay? All right, so what is x second? That is m x prime times x second. X second is minus b over m x prime minus k over mx plus k x prime. Okay? So what is that? That is minus b x prime square minus k x prime x plus k x prime. These two terms wave goodbye. So what do I have? I have minus b x prime squared. You see, this is similar result to what we got before, isn't it? When we translated the system into two system. Okay. So this is basically, again, I'm trying to show you it's the kinetic energy and the potential energy, or if you translate it, you get x1, x2, and then you can show that what 0, 0 is stable and so forth. All right. Any questions so far? Okay, and then this should be enough to show that the origin is asymptotically stable. Again, if b equals 0, then dv over dt is equal 0. That's enough for stability. But if there is a friction, b is the friction constant, and then it's a positive, then this is less than 0, and then the origin will be asymptotically stable, not only stable. All right, I'm gonna stop here today, and we'll pick it up from here. Please read what we did today. It's very important about the Lyapunov functions. And we'll continue with this. I expect to meet with you 4 more times, 2 this week and 2 next week. And we should be way done with the Lyapunov function that I want to do. I did assign a homework. I'm going to assign 1 more homework, and this is it. Okay? Any questions for me?
Yeah, I just had a quick question regarding chapter 6. Since the video kind of cut out a bunch of the stuff, I
Yeah.
just wanted to make sure. Should we look into like theorem 6.4.2 and 6.4.3 as well?
6 point. Let me go back. I need you to look at 6.42 and 6.44. Okay?
Got it. Thank you.
6.41, we did the proof and we did an example. Then do example 6.11. All right? And 6.42, don't do it. It's more advanced. I don't need you to do 6.42. And so, and I need you to look at 6.44 and then look at the example 6.13. Okay? That's all. That should be enough.
Just 641 and 644.
Yeah. Those will summarize everything. Okay? All right. Any other questions? And please try to understand. So you see the Lyapunov function was arbitrary we came up with. Usually polynomial one is what we are really interested in, or the material that we cover a lot of the time. Polynomial Lyapunov function will work. So you see in my first example, I took a x2 squared plus c x1 squared. And I said a and c are positive. I'm going to choose them accordingly. And I went through the derivative. I want the derivative to be negative. There is a mixed term, x1, x2, but you don't know the product. It could be negative, could be positive. So I need, if I can get rid of them, then I am good. And I was able to choose a and c accordingly. I got rid of the mixed terms, and I was only left with one term square, which is and with the negative sign in front. I'm in heaven, man. So I got my dv to be less than 0, and tomorrow we will show, in this case, the equilibrium solution is asymptotically stable. Okay? Any questions? And why is Lyapunov function very important? Remember, when we looked at nonlinear system, we looked at the equilibrium solution, or we linearized around, so we have x prime equal ax plus some function g, and we looked at the eigenvalue of a. But we needed that the real of a to be less than 0 or equal 0 to get something out of it. But what if 0? Then we have nothing to say about this system. Lyapunov function will tell you, will give you result about this. So Lyapunov function is more general, all right? Even though A has non-negative eigenvalues, they could be 0, which is will be center, but then the theorem about linearization says nothing about this one, but Lyapunov function will tell you it's stable, okay, or unstable, okay. So this is where we're heading. So this is a very general concept. All right, any questions? I'm gonna stop here recording and we'll take it up from here.